All right, so I'm going to make a concept map of the ideas behind the process of science or scientific inquiry. You know, we try not to call it scientific method too much at this level of education because it suggests that there are these set steps that you go through in a certain order, and then you get to the end and you know the answer, and it's like, ta-da, we're finished. But as you've seen through the other lecture material I've given you in reading, or just from like observing science, it's an iterative process, meaning that it repeats itself. And often that's like through a hypothesis, expected observations, real observations, and then evaluation of a hypothesis, and then go through that often a number of times. And also a lot of times you try to do the experiment and nothing works. So you troubleshoot, meaning try to figure out what's going wrong, if it's really a negative result or if it's just something with your technique, that kind of thing. And that can take a very long time to troubleshoot to get an experiment to actually work before you can actually decide if, answer your question. So there we go. Okay. That brings us to this concept map. So I'm going to draw and probably have to shrink and make bigger, but main topic, science and the practice of science. And I want to talk a little bit about the steps of the scientific process. There's certain things you always have to do. And one of them is to ask a question. Okay, so if there's something that you're trying to figure out in order to actually, be able to investigate it, because otherwise, what are you investigating? So after you ask that question, then you're going to tentatively answer that question. And that is what a hypothesis is. Hypothesis, plural is hypotheses, not hypotheses, hypotheses. It is a tentative or temporary or proposed answer to the question. You'd write it as a statement, as if this was the answer that you came up with in the end. At the end, you can decide if the hypothesis is supported or not supported. But technically, and for our class, you won't use the word proved or proven, anything like that, because there's always potential of having other variables involved that you don't realize are there, and thus, you may get a false result. So you can never really say proven. You could say very well supported or supported, that kind of thing. So when you write about hypotheses, I want to make sure you use that correct terminology. You get your hypotheses based on previous data. That's why it's important to read a lot, as well as to go to talks and listen to people talk about all kinds of scientific findings. It might inspire you to come up with new questions. Or you may be observing things directly yourself, and that can allow you to develop questions. So there can be an observation period where you're just like out, looking at stuff. But eventually you have to come up with a question before you can actually do science. The hypothesis has to be testable, has to be falsifiable, as in there has to be some sort of result that exists that tells you, this is not the case. If you can't measure it, and there's no way to tell if it's supported or not, then it's not a scientific question. So scientific questions cannot be explained by supernatural phenomenon because there's no way to measure that. There's no way to falsify it because the answer is always, well, it could be something we just don't know about. And, that is true, but that's not a scientific answer or explanation. You also, we're not looking at opinions or ethics when we actually talk about science, and there is bioethics, but it's different than the scientific process, where it's just telling you how things work in the natural world based off of data and observations. let's also note that a hypothesis is not the same as a prediction. We'll talk about prediction a little bit later. It's also not the same as a theory. This is a common one people use the incorrect word for. So a theory, let's define that over here. If you have more room on your paper, you can put this, it doesn't have to look exactly like this. And if you're making a concept map on your own too, it does not have to be like this. There's no really right or wrong way to make a concept map. It's just you getting your ideas connected together in a graphic format. And I would do this not to learn the material per se, but I would do this as a review to see, do I know the material? Because if you make a concept map and you can't fill it out at all, it means you gotta go back and study. Or maybe you can fill out half of it, but then you get to something else and you have no idea what to expand. Then you know, all right, I'm not gonna waste my time studying this I already know. I'm gonna go and study the part that I couldn't expand on in this concept map. And it can be of anything. I've even used them for like writing an English paper before. So theories are well established, different than a hypothesis, and accepted, well accepted in the scientific world. You wouldn't call it a theory if it was just a kind of like vague idea out there. That would be basic, that would be like a hypothesis rather than a theory. It's based off of hundreds to thousands of facts. So you already have data that helps you develop this. And if you want to define it, I'd say, oh, it's an overarching, which means broad, big idea to explain a natural phenomenon. You see stuff happening, and this is an explanation, a big, broad explanation of why it's happening and how it happens. That is what a theory is. So if you have a specific idea, that's called a hypothesis. A theory is like when you have a lot of hypotheses all coming together into some big idea. And we'll talk about a third step. So now you have a tentative answer, and now you have to test it. So that's going to be designing your experiment. And let's just talk about this right now. Let's look at this word first. All right, so you see the word experiment. E is here and I is there. So it said experiment, not experiment. Experiment would suggest that the I would be first, but that's not the case. So when you say it, you're going to say experiment. Experiment. Side note, but you know, I see it a lot that people do it incorrectly. So design an experiment. So this is the core concept of science, to actually be able to test things. That has to be done. It does not have to be done in a lab. It does not have to be done with a controlled experiment, but you have to have some aspect of testing. There are a number of approaches that you can use. And you might notice here that you might have had some misconceptions about what counts as an experiment or not. So one thing is you can just use some comparative observations where you're not actually manipulating anything directly, but you're out in the field having, you still have questions, you still have ideas about what's going on, and then you can observe and see if your observations, which still have to be data, support that idea of what's happening. So it doesn't have to be manipulating something directly. If it is manipulating something directly, usually we call that a controlled experiment. So that's another approach. In a controlled experiment, you'll have at least two groups. The control group, hence the name controlled experiment, and one or more experimental groups. Okay. What makes those groups different? The variables. So you have to have controlled variables, which we'll talk about in a second. Put it in parentheses. Let's just put this right here. Misconception. Controlled variables do not have to be constant or unchanging. You may have thought that. They do not have to be constant. They do, however, need to be matched. So you get the groups to be matched. As in, whatever, you try to make the groups as similar as possible, and what's happening to them as similar as possible, even if stuff's changing, still similarly changing or experiencing. And then you want to manipulate just one thing generally. That's the idea of a controlled experiment. So you're just getting the groups to match, even if the environment's changing, let's say. Some people think you're going to need to like put stuff in a, a sealed off room inside of a lab where the temperature is all perfectly controlled, but that's not necessary. I mean, you can do that for some things, but that's not necessary. You can do controlled experiments out in the field where there's rain some days, there's sun other days, changes. The thing is, you just have to have your control group and your experimental group or groups both experiencing sun some days and rain other days and heat other days. Like, as long as they're both the same, then it's still a controlled experiment, and you should be able to tell if it's something in the environment that's causing the effect that you didn't know about, or if it's what you're actually trying to study. And so those things that may cause an effect that you didn't realize, we call those potential confounding factors. PCFs. I don't think that's like a general PCF is like a major term, but for our purposes, in case we need to write it, we'll do it like that. So PCF, potential confounding factor. Those are the things that you're going to want to control for to match between the groups so that you don't have confounding factors. Okay. So the other types of variables, the one that you're actually testing, which is called your independent variable. So this is what the experimental group or groups is subjected to. You want to think of that. This is the difference between them. This is the thing that you think is going to make a difference. The thing you think is the important part that's answering your question. We'll see in a second. Okay. So you're going to have one or more levels of treatment to make experimental groups, and that's your independent variable, the levels of treatment. The variable itself is like temperature, and the levels of treatment would be, the different degrees of temperature. The independent variable is a drug, and the levels of treatment are no drug, 5 milligrams of drug, 10 milligrams of drug. The independent variable is amount of sleep, and the levels of treatment are 5 hours of sleep, 7 hours of sleep, 10 hours of sleep. The control group, you're going to have the level of treatment equal 0, like they don't get that at all. They don't get that treatment at all. Or it could be a known level or a normal level. So, for example, the sleep. If you're testing the effect of sleep on, balance, let's say, or something, like your hypothesis is that more sleep is going to give you greater balance. You wouldn't have the control group be 0 hours of sleep. Like, you would not set it to 0, because you know 0 hours of sleep is an abnormal condition, right? That would be an abnormally low amount of sleep, right? You might actually use that as one of your experimental groups, but you would not use that as a control group just because it's at 0. That could be an experimental group. So what would you set as control? A known value, that is a normal kind of amount of sleep, is 7 hours, maybe 8 hours, something like that. So you could set your control group at 7 hours, which is the baseline, and then see if 10 hours makes it, if your hypothesis is that more sleep makes you better balance, you'd expect 10 hours to give you better balance, and then you go down to 5 hours and see if that has worse balance than the 7-hour control. So you see how that doesn't have to be 0 or not treatment. They're still getting sleep, but it needs to be something that's either no drug or some sort of known treatment or a known condition like this 7 hours of sleep. Okay. Then the other thing to figure out if sleep makes a difference, or the drug or anything, to see if the independent variable matters. That's how I think it. Does the independent variable matter? We have to measure something. So that's what the dependent variable is. Measure, observe. Dependent variable starts with the D for data. Dependent variable is the data. It's how you're going to tell if the independent variable matters. Like, how am I going to measure balance? My dependent variable would be the number of times someone falls off a balance beam, although maybe that's a little tough because who can walk in a balance beam normally? Okay, you put a line on the ground and you're going to measure how many times the person steps off of the line. That would be my dependent variable, would be number of times stepping off the line. And then I could compare it and see, does the group that gets more sleep, 10 hours, have less steps off the line than the group who gets less sleep of 5 hours? And what's the normal stepping off the line? Like, what's the baseline amount that somebody falls off the line at 7 hours of sleep? That's why you have to have a control, because, like, let's say you have someone not falling off at all at 10 hours, and you think, wow, 10 hours of sleep, man, that's like really great. But then you have 7 hours of sleep and someone doesn't fall off either, then your 10 hours didn't make a difference compared to 7. And then if you don't do another group like 5 hours of sleep, and 5 hours of sleep also doesn't fall off the line, then that's telling you that actually less than 7 hours of sleep doesn't matter either. So it's important to have multiple groups in order to see, like, does it actually matter? Okay, so in a controlled experiment, you also want replicates. When you have, a lot of times you hear this term N, so big N equals number of subjects or number of experimental rounds, something like that. So it's telling you how many times you've investigated something, how many groups, and it's really important to have a lot of, there's certain numbers of replicates. Like with certain experiments, not people, but certain experiments, like you can do it 3 times. Triplicate is typically a standard kind of experimental number. So if you do it 3 times, you get the same result. You have a lot of confidence in that result is real. With people, you want a large subject pool. If you test something on 10 people and you get a result, mostly what that tells you is that it's something you should look into, but it's really not a lot of confidence yet with only 10 subjects. And really, with 10 subjects, even if it doesn't seem to make a difference, if it's a logical idea, it may make sense to study in a bigger group, because sometimes maybe you just got the wrong 10 people that it didn't affect. And so, there's a lot of nuances, and you have to use a lot of different aspects of your process and why you're doing things to figure out what you should do next. It's not just super obvious that, oh, we should do this or not do that. And you're kind of seeing that. I'm making this video, if you're watching this later, during the COVID-19 outbreak, the SARS-CoV-2, and you're seeing that in real time with the kinds of tests they're doing, and everybody's observing it, which is very unusual, right, for the general public to see the scientific process. And so, you're seeing when do scientists and doctors say something is real or not? How are they deciding whether to continue tests or not? There's like a lot of variation in what people think and how they do that. And so it's something to you have to really consider in your daily life too. For example, let's say you are trying to, I don't know, get stronger. Okay, so you want to get stronger. And so you can lift 10 pounds right now. And let's say your goal is to lift 20 pounds. And I'm sure a lot of you are like, please, 20 pounds. But let's just go with it. So you have 10 pounds, you want to lift 20 pounds. And one thing is, let's say what you do is you start taking protein powder. You are running to improve your cardiovascular activity. You sleep more to try to like give your muscles more time to build or something. And you, start lifting weights every day. You just change 4 things. That's the potential confounding factor issue. You have 4 independent variables now. And if you have a result like, wow, now I can lift 20 pounds, what of those 4 things did that? You don't know. So that's a whole thing of like having too many variables, too many independent variables, and you can't tell the outcome. So that would be a bad experiment. What you want to do is just change one thing at a time. So you keep your protein intake the same, but you'd start lifting every day, let's say. Or you would change the protein, but whatever your exercise routine was, you keep that the same. And sometimes, in real life, it's sort of annoying because you want to change a bunch of stuff to get a result. But if you really want to know what is causing an outcome, you really need to change one thing at a time and eliminate those potential confounding factors. It's also true that you are an N of 1. So just because something happens to you doesn't mean it's real. I mean, it feels real. But you have to, to really be confident in something is having an effect or not, you need a larger experimental pool. That being said, there are certain things that affect a small percentage of the population, potentially based off of genetics, but don't affect others. Like we're seeing this with some drugs right now. The drugs, when you look at a large population, the drug doesn't seem to work very well. But when you drill down to specific subpopulations, the drug works really well. Like let's say with cancer. Certain cancer drugs, if you tested it on a wide range of cancers, it's not going to work. At least overall, you wouldn't get statistical significance of tumor shrinkage, let's say, your dependent variable. But if you look specifically at a certain type of pancreatic cancer with a specific mutation, it works really well on that. So that's a case where your N is important, but you also have to have the right group you're looking at. Now, do you want to just go fishing and trying to find anything that correlates together? No. That's a bad process of science where you're just trying to find anything that correlates. Because remember, all these results, the dependent, independent variable, are all really correlations, not causation. So correlation means you see one thing and it tends to be accompanied by another. Someone takes the drug, it is accompanied by tumor shrinkage. Someone lifts weights every day, it's accompanied by being able to lift more weight. You can become more confident in causation the more experiments and the more data you have that support this relationship. You can become more confident in causation when you have a larger N, generally. You can become more confident in causation when you have a very well-controlled experiment where there's like you really feel very confident that there's nothing different between the groups than what you've manipulated. And then the causation becomes more confident in that. But technically everything's really just correlation. And if you look for correlation, you can find it in lots of things. Like if you're just randomly trying to correlate things. For example, I did a statistics project once, like a very large scale one, and we found a correlation between preferring Easy Mac macaroni and cheese over Kraft if you were left-handed. It was statistically significant, like pretty, high confidence interval. But is that real? It doesn't make any sense. We actually included right and left-handedness to be like a should be nothing kind of throwaway sort of group to make sure that it wasn't, so that our setup was correct. And so obviously there was something else going on. That's not a causation. So you just have to be logical about these things as well. Okay. So I will ask you to design an experiment on the exam. So you're thinking about all these aspects there and how to best design the experiment to minimize potential confounding factors and maximize good data collected. Then you come to predictions. So you have to know how you're doing the test before you can predict what the outcome would be if your hypothesis is supported. So here's how this works. So a prediction is really the expected results. Like, what do you expect the dependent variable data to look like if the hypothesis is supported? This is when you use the if-then statement. That is not a hypothesis. Hypothesis is just your answer to the question. So if, then you literally state the hypothesis again. If, what was I doing? Oh, if more sleep results in better balance, that was my hypothesis. More sleep gives you better balance. So if more sleep results in better balance, then what do I expect to see? My dependent variable. Then the group with 10 hours of sleep will have less stumbles off the line than the group with 7 hours of sleep and the group with 5 hours of sleep. You can even go and say the group with 7 hours of sleep, this is the second prediction, will have less stumbles off the line than the group of 5 hours of sleep. And both of those make sense. And that would, if that's the case in both of those groups, it would support your hypothesis. And then you do the experiment. Some other things I want to mention. Science is asking questions about how does the natural world work, meaning nature. That's really what we're asking here. I also want to add, I realized I left this out, you can be looking at groups that are just different naturally, like where something lives, or what time of year it is. What else? Let's see. How old somebody is. So it doesn't have to be something you're literally manipulating yourself. This really, that's why independent variable is just what's the difference between the groups, and that you think is actually impacting the outcome. It's not really the thing that the scientist manipulates. I know that they say it a lot, but I think that's misleading, because it leads people to think that the scientist has to be in charge of controlling everything and then, only changing one thing and all that. But you do want the groups to be as matched as possible, but this may be in nature, not actually in the lab being manipulated physically. Often students get a question about this kind of idea wrong, so I want to go over it. So examples of observational approaches that are not controlled experiments, but that are science, because they ask questions and answer it with prediction or hypotheses, and then figure out ways to measure data and then predict what the outcome would be if the hypothesis is supported, and then see if that's the case. So something like birds evolved from dinosaurs, which is supported. And that's in the past. It's not like you're literally manipulating them today, and that's okay, because there are ways to measure or collect data to suggest if birds are closely related to dinosaurs or not. And we can even use stuff like looking at, other reptiles, right? Because we know those are in the dinosaur group, and see how birds fit in genetically with them. And then look at fossils to see if birds are behaviorally doing similar things to what you see in dinosaur fossils. And then you can look at the morphology, the physical features of birds and dinosaur fossils. There's like the skeleton, and you see similarities there. So even though it's in the past, this can be a scientific question and can be studied with data. Even events in the past can be studied. Dinosaurs went extinct from an asteroid hitting the Earth. That is well supported. What kinds of things did they measure? Asteroids bring in certain elements that are not readily present on Earth, like iridium. And so what do? You go search for iridium in the layer between, or in the layer of rocks where the extinction of the dinosaurs happened. And they found it. And there's tons of evidence in all chemistry and geology, physics, biology that are all suggesting and support this idea of an asteroid causing the extinction that included the dinosaurs, even though it happened in the past. The finding that DNA was a double helix. That wasn't manipulating any two groups, but it used data and predictions and hypotheses to figure out what are the measurements that should be seen if the DNA is a double helix. And then let's find the measurements, and do we see that that is supported or not? In fact, they thought initially it was a triple helix, but the measurements didn't support that. And so then they had to reject that hypothesis and come up with something new. You can even look at things like behavior in chimps in this case. So chimps have a hierarchical social structure. Not manipulating anything, but you can look at the behavior of the chimps. You have to have things to measure though. So you can't just look at it and say, yeah, I think this is what's happening. There has to be something where you're looking at interactions between different members, let's say. And do these certain members, do they all interact together equally? Or are there some that only seem to be interacted with by others? Suggesting maybe like the head of the hierarchy is not in contact with the lowest in the hierarchy, maybe only in the sub-hierarchy, something like that. And so that starts to tell you there's layers of stratification in the chimpanzee society. You could look at mating, right? So does one or a few different males get to mate with the females, suggesting that there are males that are in a different sort of level than other males? Or is it open mating to where all the males can find a mate with equal likelihood? So those are observations based off of data. And I mean, I don't even know if those are things they look at. I just came up with those on my own because I'm using logic of what might be reflecting of a hierarchical structure based off of previous knowledge I have of hierarchies, and coming up with hypotheses and then predictions of, if this is a hierarchical structure, what should I see those dependent variables like communication pairings, what would I see as the result? And that's my prediction. If there's a hierarchical structure, which is my hypothesis, then certain males will get to mate with females more often than other males, or males in the higher in the hierarchy will get to mate with females than other males. And that is a scientific question. So I want to mention that because sometimes really people have this misconception of scientists in a lab and white lab coats mixing stuff together and then, you know, coming up with an answer and being isolated. And I'll tell you, science is a very not isolated process. You're probably not doing it right if you're not chatting with people and meeting with people and, you know, going to conferences and hanging out, because that's where the ideas come usually, is when people are just hanging out, talking about their science, excited about things, find something new, talking about something they heard somewhere else, and then ideas come together that would never have come together if you just sat in, you know, your little bench by yourself. And that's when you really get some cool scientific findings and real advancements, I think, is when the collaboration happens. Plus, it's more fun.